The most expensive repair on a modern turbocharged engine is usually not the engine block. It is the turbocharger. Replacement costs on most passenger cars run from $1,500 to $4,000, including labor. And the majority of premature turbocharger failures trace back to the same two moments in the engine's operating cycle. The first is cold start, when the bearings are already spinning before oil pressure has built throughout the lubrication circuit. The second moment is one that surprises most turbocharged engine owners when they hear it for the first time. The most dangerous moment for a turbocharger is not when you are pushing it hard. It is when you turn the engine off after a hard drive. A turbocharged engine and a naturally aspirated engine do not face the same oil challenges. Full synthetic motor oils that provide completely adequate protection in a naturally aspirated engine can fall short in a turbocharged application. Because the thermal stresses on the oil are categorically different, turbocharged engines have three specific failure modes that naturally aspirated engines do not face at the same severity: heat soak and carbon deposit formation inside the turbocharger at shutdown, a specific combustion event called low-speed pre-ignition that can destroy a turbocharged engine in a single drive cycle, and intake valve carbon buildup accelerated by the gasoline direct injection systems that most modern turbocharged engines use. The best synthetic oil for a turbocharged engine is the one engineered for all three of these failure modes, and not every product marketed for turbo protection addresses all three. Here is why the turbocharger is where the oil decision shows up most concretely. A modern passenger car turbocharger spins at speeds between 100,000 and 250,000 revolutions per minute. The bearings that allow the turbine and compressor wheels to spin at those speeds are lubricated by the same engine oil circuit that feeds the crankshaft and camshaft bearings. The oil at those turbocharger bearings is doing its job under conditions more extreme than anything else in the engine, including high heat, extreme rotational speed, and a very narrow oil film between metal surfaces that are moving faster than any other part in the drivetrain. When that oil film breaks down, metal contacts metal at 200,000 revolutions per minute. The damage is not gradual, it accelerates. At every cold start, there is a window measured in seconds when the oil pump is pressurizing the lubrication circuit, and oil has not yet reached every bearing surface. In a naturally aspirated engine, this cold start window primarily concerns the camshafts and crankshaft bearings located close to the oil pump. In a turbocharged engine, the turbocharger sits at the end of the oil supply circuit, often mounted directly on the exhaust manifold at the farthest point from the oil pump. Oil reaches the turbocharger bearings last at every cold start. An oil that flows quickly at low temperatures, specifically one with a strong cold flow characteristic reflected in the first number of its viscosity grade, reaches those bearings faster and reduces the metal contact window that exists at every single startup. Now here's the shutdown failure that most turbocharged engine owners have never been told about directly. When you drive a turbocharged vehicle under moderate to hard load and then pull into a parking lot and shut the engine off, the oil pump stops. The turbocharger has been spinning at high speed. The exhaust turbine housing, the part exposed to hot exhaust gases, has been operating at temperatures exceeding 800 degrees Celsius. When the engine shuts off, the turbine housing does not cool immediately. It continues radiating heat into the turbocharger's center section, the housing that contains the bearings and the oil passages that feed them. The oil remaining in those passages is no longer circulating. It is sitting stationary in a housing surrounded by residual heat from the exhaust side. That heat bakes the stationary oil into solid carbon deposits, a process called coking. These deposits accumulate in the narrow oil passages of the bearing housing with each hot shutdown. Each layer further restricts the oil flow to the bearings on the next cold start. The restriction is not immediately noticeable in the driving experience, but the turbocharger that eventually fails with blue smoke on cold start and a grinding noise under acceleration has typically been accumulating coking deposits for tens of thousands of miles, one hot shutdown at a time. The resistance to coking is directly determined by the thermal stability of the oil's base stock. An oil built on a pure base stock, specifically the gas-to-liquids technology that Shell uses to produce Pennzoil Ultra Platinum, resists thermal degradation in stationary heat-soak conditions, measurably better than a petroleum-derived Group 3 synthetic at the same viscosity grade. The pure base stock does not contain the trace sulfur compounds, aromatic hydrocarbons, or wax molecules that accelerate coke formation under heat. At the extreme temperatures inside a turbocharger bearing housing at hot shutdown, base stock purity translates directly into fewer deposits in the oil passages and longer bearing life across the vehicle's service life. Here is the second failure mode, and it is the one serious enough to drive the development of an entirely new motor oil certification standard for the 2026 model year. Low-speed pre-ignition is an uncontrolled combustion event that occurs in turbocharged gasoline direct injection engines at low engine speeds under high load, exactly the moment a driver accelerates hard from a slow speed onto a highway. Droplets of oil and fuel in the combustion chamber ignite before the spark plug fires. The pressure spike from an uncontrolled combustion event is orders of magnitude higher than a normal combustion event. In severe cases, a single low-speed pre-ignition event bends a connecting rod, cracks a piston, or punctures the cylinder wall. In the mild cumulative form, it occurs across thousands of drive events without the driver noticing anything, and each event removes a fraction from the structural integrity of the piston and connecting rod until catastrophic failure becomes the outcome of what looked like normal driving. The chemistry connection that most oil buyers have never heard is that traditional calcium-based detergent additives in motor oil, the compounds that clean engine deposits and neutralize combustion acids, promote low-speed pre-ignition in turbocharged gasoline direct injection engines. The same additive chemistry that makes conventional full synthetic oils. Effective at keeping engines clean is part of the mechanism that generates the droplets that cause uncontrolled combustion events in these specific engine types. The GF7 motor oil certification standard, introduced for the 2026 model year, was developed specifically in response to this. GF7 requires that certified oils meet low-speed pre-ignition resistance standards, not just when the oil is fresh out of the bottle, but after the oil has been working in the engine for the equivalent of a full drain interval. An oil that protects against low-speed pre-ignition on day one, but loses that protection at 5,000 miles, is not solving the problem the engine faces at 7,000 miles. The GF7 aged oil sequence test measures whether the protection holds throughout real-world use. Pennzoil Ultra Platinum is GF7 compliant, and its Pure Plus base stock's thermal stability contributes to maintaining that protection through the drain interval rather than degrading toward its end. The third challenge specific to most modern turbocharged engines is the gasoline direct injection deposit problem. Engines with direct injection spray fuel directly into the combustion chamber at high pressure, rather than through the intake port. Because fuel does not pass through the intake port, it does not wash the back of the intake valves the way port-injected engines do. Combustion byproducts and oil vapors from the positive crankcase ventilation system deposit carbon on the intake valve faces and stems without the natural cleaning that port injection provided. Turbocharged engines produce more crankcase pressure than naturally aspirated engines, which increases the amount of vapor that feeds back into the intake tract and deposits onto those valves. An oil with stronger detergent chemistry and a cleaner base stock reduces the rate at which those deposits form. Pennzoil. Ultra Platinum's 65% piston cleanliness advantage over the industry minimum is a direct measure of the oil's effectiveness at limiting these combustion chamber and valve deposits over time. Here is the decision framework for owners of turbocharged engines. If your vehicle is a turbocharged gasoline direct injection engine and it is a 2023 or newer model, GF7 compliant motor oil is the specification your engine was engineered around. Pennzoil Ultra Platinum, or another confirmed GF7. Compliant synthetic at your manufacturer's specified viscosity grade is the correct choice. The low-speed pre-ignition protection in GF7. oil is not a marketing upgrade for a new engine. It is the standard the engine design assumes is in the crankcase. If your turbocharged vehicle is a 2015 through 2022 model, GF7 compliance is not a factory requirement, but it is a genuine improvement over the prior GF6 standard. Low-speed pre-ignition occurs in all turbocharged gasoline direct injection engines, regardless of model year. GF7's enhanced and interval-tested protection applies directly to these engines. Using GF7 compliant oil in an engine designed for GF6 is safe and provides measurable additional protection for the failure mode these engines actually face. If you have been extending oil change intervals on a turbocharged engine beyond 7,500 miles, the thermal degradation rate in a turbocharged application is meaningfully higher than in a naturally aspirated engine of comparable size. The oil that has been exposed to hundreds of hot shutdowns and repeated heat soak cycles reaches the end of its additive effectiveness faster than the same oil in a calmer operating environment. 7,500 miles is a practical upper limit for most turbocharged daily drivers, and 5,000 miles is the more conservative target that several turbocharged engine manufacturers specify in their maintenance schedules. The price of one additional oil change per year costs a fraction of a single turbocharger replacement. If your turbocharged vehicle produces a brief puff of smoke on cold start that clears as the engine warms up, this pattern is consistent with progressive coking deposit buildup in the turbocharger oil channels. The deposits restrict oil flow at cold start, cause momentary reduced lubrication in the bearing housing, and the resulting friction produces the startup smoke. Switching to Pennzoil Ultra Platinum and maintaining 5,000-mile change intervals slows further deposit accumulation. In severe cases where deposits have been building for years, a turbocharger flush service that runs solvent through the oil circuit can address existing buildup before oil quality improvements take full effect. If you habitually shut off the engine immediately after arriving at a destination following sustained highway driving, allowing the engine to idle for 60 to 90 seconds before shutdown, gives the turbocharger time to reduce speed and temperature below the threshold where stationary oil begins to coke aggressively. Many vehicles produced after 2015 use water-cooled turbochargers, which reduce heat soak severity at shutdown. The water jacket continues carrying heat away from the bearing housing after the oil pump stops. Water cooling reduces but does not eliminate the coking problem, and the oil quality recommendation does not change regardless of turbo cooling design. Good oil and a good turbocharged engine are not the same relationship as good oil and a good naturally aspirated engine. In a naturally aspirated engine, the gap between adequate full synthetic and exceptional full synthetic shows up in deposit counts and wear metal readings at extended drain intervals. In a turbocharged engine, that gap also shows up in whether the oil resists coking at shutdown temperatures that exceed what any other engine component faces, whether the additive package maintains low-speed pre-ignition protection through a complete drain interval under thermal stress, and whether the base stock purity is sufficient to keep the intake valve deposits and combustion chamber residue below the threshold where the engine's performance begins to degrade. The turbocharger is the most thermally stressed component in a modern passenger car engine. The oil that reaches it first at cold start stays with it through every heat cycle under load. The oil that protects it at the moment of shutdown is the single most consequential maintenance decision in that engine's service life.